If we're given a random variable, we'll call it x, which is distributed binomially with some n and some p-value. We went through the process of determining the probability that x is equal to some value. And to determine that, we just need to find an n. We'll say n is equal to 10. And some p-value, we'll say p is equal to 0.5. And we plug these values into our formula for p of x, and it will determine the probability that x is equal to some value. We'll say x is equal to 5. Now, this process is relatively straightforward, and it's even relatively straightforward if we have multiple values of x. We'll say x is equal to some range. We'll say 5, 6, and 7. Then we just need to plug in our different values of x into our formula, and then sum the values together. So we plug in x is equal to 5, x is equal to 6, and x is equal to 7, and sum all those probability values together to determine the probability that x is equal to 5, 6, or 7, with n equals to 10 and p equals to 0.5. Now, what happens if we have a much larger value? We'll say n is equal to, we'll go with 10,000. If n is equal to 10,000, this process is still relatively straightforward. We just need to change our n in our formula and plug in our same values for x, and just need to do it 3 different times because we have 3 values for x, sum all those values, and we get our answer. However, what if x is much larger as well? We'll say x has a range from 5 up to, we'll go 5,000. This becomes a much more complicated process. You need to plug in every single one of those values for x into our formula and use that to determine the probability that x is equal to that range. Now, there's got to be an easier way to do this, and that's the purpose of this video, and we're going to find a way to do that in a much more simple fashion. For our binomial example, let's set our n value equal to 10, and our probability of a success is equal to 0.5. And if we do that, we get this histogram that we see on the bottom, where 0 is almost no chance of happening, and we go all the way up to 5, which has about a 25% chance of happening. Now, if we just get a general idea of the shape of this distribution, just kind of draw an overview line, it looks very similar to our normal probability distribution. It's got this nice bell-shaped type curve. So we're going to use this resemblance to the normal probability distribution to estimate the binomial probability distribution for larger samples. So if we have a random variable, we'll go with our x is distributed normally. It takes a value of mean, of mu, and a standard deviation of sigma to determine what that normal distribution is. So if we're trying to approximate our n equals 10 and p equals 0.5 distribution with this normal distribution, how are we going to do that? Well, we need a value for mu, and we need a value for sigma. When we went through the binomial distribution, we actually came up for values for these. We found that the mu is equal to n times p, which is in our case equal to 10 times 5, or 0.5, which is equal to 5. And then our sigma was n times p times q, and then the square root of those values, which is equal to the square root of 10 times 0.5 times 0.5, which is equal to the square root of 10 times 0.25, or 2.5, which is actually just equal to about 1.58. So we just need to use these values. So n is distributed normally with a mean of 5 and a standard deviation of 1.58. And we can use that to help estimate our binomial probability distribution. If we're going to use our normal probability distribution to estimate our binomial distribution, we'll say we're trying to find the value, the probability that x is greater than, we'll go with 7. Now, how would we do that with our estimation technique? So if we were going to do it with just the standard binomial probability distribution, we would be looking for the area under the curve that's approximately equal to this. So if we look at that and we're trying to approximate that with our normal probability distribution, we actually have some potential discrepancies. Since our 7 value actually resides right here, if we're trying to find the probability with our normal distribution, it would actually be finding the probability that's going just to this region only, and then all this way. We actually need to adjust our z-score that we're going to be using to find our standard normal distribution for our binomial distribution by 0.5. We need to jump it up to the 7.5 region up to here so that we get that full bar for all the 7s. So to continue on our example, for probability x is greater than 7, we know that that's actually equal to the probability that x is greater than or equal to 8, which is also just equal to 1 minus the probability that x is less than or equal to 7. So using our slight modification, we're just going to try to find what 1 minus the probability that x is less than or equal to 7.5 is, using our normal approximation. So if we then just find the z-score of our 7.5, so we have 7.5 minus 5 divided by our 1.58 for our standard deviation, we get 2.5 over 1.58, which is actually equal to about 1.58 again. Then we look up our 1.58 value in our normal probability distribution table. And if we do that, we get 1.58 is approximately equal to 0.4429. So we have 0.4429 plus our 0.5, because our normal probability table just does from the mean up, so plus 0.5. And then we have 1 minus that value. So we have our 1 minus our 0.4429 plus 0.5 in parentheses. So we have 1 minus 0.9429. So we get our probability that x is greater than 7 is approximately equal to 0.0571. And if we were actually to go out and do this using our binomial probability distribution, we would have actually gotten the value of 0.05469. So if we look at those two values, our 0.05469 and our 0.0571, those are actually relatively close. And if our n value gets larger, those approximations will get much closer to our actual value. So much so that they're basically indistinguishable once you get to a high enough n value. So we now have a relatively easy way of approximating a binomial probability distribution if our n value is big enough, using just our normal probability distribution techniques.